So what happens when we start talking about 3 dimensions and vectors? Now, you recall from 2 dimensions, we had these things called unit vectors. And a unit vector is simply the vector that's in the same direction, but with length 1 or magnitude 1. So if I want the unit vector of A, remember the symbol is that, let's call that a caret, that symbol, with the caret on top. The unit vector for A is simply A, but divided by its magnitude, thus ending up with a magnitude of 1. But there are 3 special ones now. In 2 dimensions, we had 2 special ones. Now, see, when we were dealing with 2 dimensions, we would have said, we want one in the horizontal direction and we want one in the vertical direction. So the x-axis and the y-axis conveniently. When you're talking about 3 dimensions, it's now the question is, well, what's vertical? What's horizontal? Because you can rotate however you like. What we say is, we want these 3 vectors to be orthogonal. And orthogonal simply means mutually perpendicular. So all 3 of them are perpendicular to each other. So we get that picture that I had, let's say for convenience, we use that Cartesian space for it and bring it back to that traditional idea of horizontal, vertical, and so on. But of course, now y is not vertical if I've got it in that orientation. So that's why we sort of avoid using the words horizontal and vertical and things like that. So you'll remember that was the one we defined in the x direction. But given the diagram that I drew the other day for the Cartesian space, it would be going in that direction. Y, it's still j, goes off in that direction. And now we have a third one, k, which is going up. Well, it looks like it's going up the way we're looking at it. How do we write our vector? What's it look like? There's my 3-dimensional space, and I have some vector there, and it's going off to the point x, y, z. Right. U with the tilde underneath, it's still the same notation as 2 dimensions. We're not changing that. OP, still, we're saying that's the position vector. That's not going to change. We no longer have the ordered pair. We now have the ordered triple. A column vector, I personally prefer using column vectors with this stuff. But there is also component form when you break it up into its 3 components. So again, pretty much the same as we saw in 2 dimensions, just pushing it through to the 3rd dimension. The length of the vector, square root of x squared plus y squared, z plus z squared. So we've got a parallelogram. It's now sitting in 3 dimensions. The coordinates a, b and d have been given. We want to find the vectors a, b and a, d. Once again, the ideas have not changed from 2 dimensions, or from complex numbers for that matter. We want to find a vector, head minus tail. So AB, and I say I'm using column vectors here, so 18, 4, 8, minus 4, 2, 3, so 14, 2, 5. 14, 2, 5. AD, negative 1, 12, 13, minus 4, 2, 3, we get negative 5, 10, 10. So head minus tail, still the same idea. So where is C in the space? So we end up, what we're basically saying is if we were to join these 4 points, they'd all lie on one plane, and on that plane we've got a parallelogram. Okay, well if it's a parallelogram, the rules of geometry do not change. Opposite sides are equal and parallel. Or if we're talking about a vector, we're saying the opposite vectors must be the same vector. So I'm going to say AB is the same vector as DC. So head minus tail must equal head minus tail. Although I've got it the other way around for some reason, it doesn't matter. C minus D would be B minus A. C is the point we're trying to find. So all I've got to do now is substitute into this. C is B minus A plus D. And so I will have for an X value, 18 minus 4 plus minus 1. Then for the Y value, 4 minus 2 plus 12. And so on, and so on, and we get our answer. So there's the point C. Whilst I said earlier that this is not a course on coordinate geometry, it's a course on vectors. But we can still use vectors to solve traditional coordinate geometry problems. Midpoint being classic, and so on. But we could divide an interval up into any ratio we like. We know a midpoint is dividing an interval in the ratio 1 to 1. Okay? So you can divide an interval any ratio, but the other thing with dividing an interval, it doesn't have to be divided internally, you can divide it externally as well. So here's an interval, AB. There's some point in between A and B, and we say that point divides it internally because the point's in between the 2 points. And the ratio m to n. So there we go, it's in the ratio m to n. Now the naming of the ratio and the interval is crucial because they must be in the same order. So this is dividing AB internally in the ratio m to n. I could have said it divides BA internally, but it would be in the ratio n to m. So the order remains the same. Okay, well, what's external division? Well, that's when you produce the line to another point. Now that point still creates a ratio when you take the distance to A and the distance to B. But that's what we call an external ratio. So it's externally in the ratio. Again, the order is important. So from P to A would be M, from P to B would be N. So you still do it the same way. So if P divides AB in that ratio, there's our formula. And the advantage of vectors is I don't have to worry about is this 2 dimensions, 3 dimensions, for that matter 4 dimensions, 5 dimensions, 6 dimensions, because a vector can be in any dimensions that you like. You just have to have the however many components. So it's consistent. P would be 1 over m plus n. So we add the numbers together in the ratio. And then you'll notice we multiply the other vectors, A and B. But it swaps around. Okay? So the A to B is m to n. So when I'm doing that multiplication there, I multiply the A by the n. So the first one with the second one. And I multiply the B with the M, so the second one with the first one. So in those parentheses there, it's opposite to the order of the ratio. And so A, B and P are the respective position vectors. All right, so let's try it. So we're going to find the coordinates of a point that divides this interval, and it's joining -3, 4, 1 and 5, 6 in the ratio 1 to 3. Well, 1 and 3 is 4. I suppose you didn't need me to tell you that, but it is. So the bottom of the fraction is 4. Now the top of the fraction, swap the ratio round. So instead of 1 to 3, you'll notice the numerator of my fractions is 3 to 1. And then I just multiply it by the respective points. And so there it is, 1, 9 on 2, 3 on 2. So that's our point that we're looking for. 1, 9 on 2, 3 on 2. External, we think of it as a negative ratio. So if they tell me it's dividing it externally in the ratio 5 to 2, I make one of the numbers negative. It doesn't matter which one, the ratio just has to be negative. Same as with a fraction. It doesn't matter whether the numerator's negative or the denominator's negative, it's still a negative fraction. Same idea. So all right, so it looks like I've chosen to do it as 5 to -2. And I probably did that so the denominator ended up positive. It's probably the only reason I put the negative on the 2, to be honest. So the denominator is 3. Swap the ratio around to get the numerator. I've put the negative on the 2, so it's -2/3. And then the other one is +5/3. And then we multiply them by the other position vectors. And there's our answer. So it's 13, 4, -9. All right. That'll do us for that piece of,